Hey everyone, and welcome back to Central Physics Reviews. In this video, we're going to be taking another look at conserved quantities, or in other words, quantities that don't change when our system evolves over time in certain circumstances. Now, we already talked about conservation of energy and momentum in a previous episode, but back then, our scope was limited to thinking about systems that were moving in a straight line without any rotational motion at all. Let me quickly remind you what some of the key takeaways are from that episode. First, conservation of energy. This occurs if there are no non-conservative forces doing work on the system. So non-conservative forces are essentially contact forces like friction or normal forces that can add or subtract from the energy of your system if they act in the same direction as its motion. So the idea here is that if none of those kinds of forces are at play, if the only forces that are acting on your system are those that convert between kinetic and potential energy, like gravity or spring forces or even electric forces, then energy itself will be conserved. And the formula we talked about for energy was 1/2 mv squared, that's the kinetic energy, plus whatever potential energy corresponds to whatever particular conservative forces are acting on your system. The second conserved quantity we talked about for linear translational motion is momentum. And momentum is something that's conserved if there are no external forces acting on your system at all. Or to be a little bit more technical, if there are external forces, they all have to cancel out for momentum to be conserved. So there can't be any net external force. And what we said in our previous episode was if that criterion is met, then the momentum of your system, which is defined as its mass times its overall linear velocity, will be conserved over time as well. Or if your system is comprised of multiple objects, then summing up their momentum will give you a total momentum that's conserved over time. And as we've seen before, knowing that these two quantities are conserved over time can be extremely useful, because it gives us shortcuts to predicting what a system will look like in the future or what it looked like in the past without having to consider a ton of microscopic interactions and figuring out how all of those forces come together. But now that we've expanded our horizons, now that we know that this isn't the only kind of motion we can have, right? We can also have rotating objects. How do these conservation laws change for a system that's rotating instead of just moving in a straight line? Well, conservation of energy works in practically the same way, except now the kinetic energy of our system, instead of being 1/2 mv squared, is replaced by this new quantity, 1/2 I omega squared, where I is the moment of inertia. It's basically the analog of mass for rotating systems, and the subscript ax here just means it's the moment of inertia with respect to whichever axis the object is rotating around. And omega is its rotational velocity, so obviously the rotational analog of velocity. And as it turns out, momentum also gets a rotational analog. For obvious purposes, it's called angular momentum, and in fact, even the formula is analogous. We can see that the angular momentum, denoted by the letter L, is given by I omega, where I again plays the role of m and omega plays the role of v. So this is a bit of a beginner's cheat sheet to conserved quantities for translational and rotational motion separately, but in this video we're going to be diving a little bit deeper than just these formulas. In fact, our goal for this video is going to In fact, our goal for this video is going to be to think about these conserved quantities for a system that's not just moving in a line or just rotating, but actually moving translationally while also rotating at the same time. And along the way, we're going to rederive these formulas, but then also add to them to get the more general, complete picture of conservation laws in mechanics. So let's go ahead and start by considering momentum conservation for a system that's both rotating and moving at the same time. Now we have here a disk, although it could really be any two-dimensional object, rotating with angular speed omega and moving as a whole with linear velocity v0. And what we want to do is we want to calculate the total momentum of this system, because we know that if you sum up every individual piece of momentum of every particle in this object, that sum is going to be unchanging unless there's a net external force, as we just said. So let's go ahead and do that calculation. So to find the momentum, we're going to actually end up doing an integral over all of the infinitesimally small momenta corresponding to all of the infinitely many points on this disk. So if we integrate over every momentum on the disk, that's going to be an infinitesimal mass, dm, multiplying the velocity of each point on the disk. And in order to evaluate this integral, what we're actually going to do is express the velocity v as a sum of the linear velocity, v0, plus the velocity component of each point on this disk from its rotational motion, which we know from the last episode is going to be omega cross r, where r is the distance to whichever point we're talking about. So to illustrate this sum, if we're considering the point over here, for example, we know that the rotational motion of this object is going to give it a tangential velocity going roughly in this direction, and the magnitude of that velocity will be omega cross r, where r is this distance over here. So the net velocity of that point will just be v0, the arrow pointing to the right, plus omega cross r, the arrow pointing tangentially. That's all we've written down here. So if we separate this into two integrals now, the first integral is going to be the v0 vector multiplying the integral of dm, and we get to factor out v0 because it's constant through all the points. And the second integral that we get is going to be omega cross the integral of r dm. And again, omega is something we get to factor out of the integral because all of the points are rotating with the same angular velocity vector omega. Now, both of these integrals actually represent something physical. The first one, the integral of dm, is just the total mass of the system because you're adding up all of the infinitesimal masses of each point in the object. So we get v0 times the mass of the object, whatever it is. And the second integral, so we have omega cross this second integral, which actually represents a sort of average position of this object because we're summing up all of these different r vectors, so it's going to point somewhere in the middle. And in fact, because we're weighting it by this factor of dm, the position that we end up getting is called the center of mass. So we're going to end up taking the cross product with the position of the center of mass, and then we also have to multiply by the total mass of our object. So just to make that more concrete, what we said was we basically defined this vector r center of mass, the position of the center of mass, as this integral we had, r dm, over the total mass. And for something as simple as a disk, you don't actually have to do that integral to find the position of the center of mass, because it's intuitively in the center of the disk. Now, if we factor out the mass here, what you'll see is we get our first term, which is just the overall velocity of this object, v0, plus the second term, which is omega cross rcm, which you'll remember is just the velocity of the point at r relative to whichever axis we're rotating about, right? So this is the velocity of the center of mass relative to the axis of rotation. And because the axis itself doesn't move from the rotation, it only moves with v0, what we're really adding up is the velocity of the axis plus the velocity of the center of mass relative to that axis. And that just gives us the total velocity of the center of mass. So the upshot is, if you have an object undergoing some complicated rotational and translational motion, if you want to calculate its momentum for momentum conservation purposes or otherwise, all you actually have to do is keep track of how the center of mass point is moving over time. And that's the velocity that you can use to calculate the momentum of your object. Okay, now let's move on and talk about energy. And we're going to do this in two different steps. The first is we're going to quickly rederive the formula for kinetic energy when you just have an object rotating about some axis. That's the top picture. And the second thing we're going to do is we're going to tackle the more general case of an object rotating and moving at the same time. So this first case is actually quite straightforward. The total kinetic energy of this object, be it a disk or anything else, is going to be the sum, or in this case the integral, of all of the kinetic energies of its individual points. So we can say 1/2 times dm for an infinitesimal mass of those points, times the velocity at those points squared, integrated over every point on this disk. But by now we should probably know by heart that this velocity vector can be expanded as omega cross r, where r measures the distance from whichever axis we're rotating about, right? And so then we have to square that. And because omega and r are always perpendicular in this two-dimensional context, we get to just write this as 1/2 times the integral of dm omega squared r squared. And what you'll recognize, if we pull the constant omega squared out of the integral, right, because all points are moving with the same angular speed, this is just the integral of dm times r squared, which we've seen before, and we've called it the moment of inertia I. And because r measures the distance from our axis in particular, we should label this moment of inertia to clarify that it's the moment of inertia relative to that axis. So we've recovered the 1/2 I omega squared that we originally saw at the beginning of this video. But what happens in this second case when we also have translational motion on top of rotational motion? Well, the first thing we need to change when we're doing this integral is replace omega cross r with our new velocity, which is omega cross r plus v naught. So maybe I'll write it this way, v naught plus omega cross r. That's our new expression for velocity, and that's what we have to square. So expanding this out, we get 1/2 integral dm of v0 squared plus omega squared r squared plus 2, and this is where you have to be a little bit careful because we're doing vector multiplication, right? We get 2 v0 dot product with omega cross r. So now if we write out these integrals, the first one we're going to get is 1/2 m v0 squared. The second term is going to give us the same thing we found above, right? 1/2 I axis omega squared, right? Because we're still measuring distances from whichever axis we're rotating about. So we have to call that integral I axis. And in this third integral, what's going to happen is the 1/2 will cancel the 2, first of all. Then we get to pull v0 dot out of the integral. Then we get to pull omega out of the integral because it's also a constant. So we get omega cross out of the integral. And we're left with the integral of dm times r vector, which, as we've seen before, is just the position of the center of mass multiplied by the mass of our object. Now, the next step in simplifying this is going to be a little bit less obvious, but bear with me here. We can write down the quantity 1/2 m times v0 plus omega cross rcm quantity squared, and add 1/2 times this moment of inertia minus mrcm squared multiplying omega squared. So this is a massive rearrangement of the equation we just had, right? All of these things are continually equal to each other. But, you can either take my word for it, or you can actually check at home that if you expand this out, you get the same thing we had on the line before. And the reason we rewrote that line in such a seemingly complicated way is because these quantities have physical meaning as well, right? For example, this is 1/2 m times the velocity of the center of mass squared, right? Because just like we've seen before, adding v0, the velocity of our axis, to omega cross rcm, the velocity of the center of mass relative to that axis, just gives us the total velocity of the center of mass. Now this second term is also interesting, because here we have the moment of inertia about the axis that we're rotating about minus m times the distance to the center of mass squared. And that might ring a bell because this is actually a combination that came up when we talked about the parallel axis theorem, which says that the moment of inertia about an axis parallel to the center of mass minus m times the distance to the center of mass squared actually just gives you the moment of inertia calculated with respect to the center of mass. So that means the same formula we used before for the moment of inertia, right? Just the integral of r squared dm. But this time, r measures the distance from the center of mass. That's the difference between I sub cm and I sub axis. And then the last part of this is just the omega squared. So the upshot of this result is that if your object is rotating around any axis, I know in this picture I drew it right in the middle, but it can be any axis, and it's moving linearly, so it's in the most generic, complicated possible motion, you can always find its kinetic energy by just summing two things. The first thing is the translational kinetic energy of the center of mass, so 1/2 mv squared, where the velocity is just how fast the center of mass point is moving. And the second contribution is 1/2 I omega squared, but also around the center of mass, right? The moment of inertia is with respect to the center of mass. Now it's true that when an object was just rotating around some axis, we used the moment of inertia about that axis, not the moment of inertia about the center of mass. But what's happening here is we're actually breaking down the motion into the motion of the center of mass and the motion about the center of mass. So that's why this different moment of inertia appears in this context. And importantly, the two formulas are not contradictory, right? If you have an object that's just rotating about some axis that isn't the center of mass, or isn't through the center of mass, I should say, then this generic formula at the bottom will actually still get you the same answer as 1/2 I omega squared using the moment of inertia about the axis itself. So if there were only one formula you could come out of this remembering, it would be that the total kinetic energy of a system is that translational energy of the center of mass plus the rotational energy about the center of mass, just like we wrote down in this last equation. Okay, now finally, let's talk about this new quantity called angular momentum in the same two steps, first with an object that's just rotating, and next with an object that's rotating and moving at the same time. To motivate what we're going to do, I wanted to start with a reminder of how we derived conservation of momentum. We basically said that the external force on an object, F external, was going to equal the time derivative, so d over dt, of something called momentum. And we concluded that if there is no external force, then there is no time derivative of momentum, and so momentum has to be constant. So what we're about to do now is we're going to write down the torque on a system, the external torque, and we're going to try to write it down as a time derivative of something. But whatever that something is, we'll know that it's a constant whenever there's no external torque. Okay, so let's get started. We know from the last episode that the most generic possible thing we can write down as an expression for torque is the integral of r cross df. Now, technically, torque can be calculated with respect to any point, because you can measure this distance r with respect to any origin of your choosing. But when we're thinking specifically in the context of conservation of angular momentum, then we want to use an origin about which there generally aren't any net external torques. And the best origin to use for that case is the position of the axis itself. Because even if the axis exerts a force on our system, the axis can't exert any torque on it because it would be a distance 0 away from that origin, and torque is force times distance. So for that reason, what we're actually going to calculate here is the torque with respect to the position of the axis. And that means that this variable r is measured from the axis. Okay, so that was a bit of a side point, but it was a very important side point to mention. So let's keep going. We can replace inside this integral df with acceleration, a times dm. That's just using Newton's second law. And then we're going to be a little bit sneaky. We're going to use the product rule to show that this is actually equal to the time derivative, so d over dt, of the integral of r cross v dm. And so let me quickly explain to you why we can do that, right? If we take the time derivative, d over dt, of the total cross product, r cross v, what we'll actually get is two separate terms, right? It's going to be dr dt cross v plus r cross dv dt. Now the term on the right, r cross dv dt, that's just r cross a. That's the same thing we had before. The term on the left, dr dt cross v, that's actually v cross v, right? Velocity is dr dt. And v and itself are always going to be aligned in the same direction, so their cross product is going to go to 0, because it measures how perpendicular two vectors are in a sense, right? There's a factor of sine theta that goes into every cross product magnitude. So this is precisely why our expression r cross a is equivalent to the time derivative of the whole product r cross v. And then of course we can pull the time derivative outside of the integral because the order of those doesn't actually change our answer. And so now what we have is actually exactly what we were looking for. We have that the external torque is equal to the time derivative of something. So instead of keeping this funky notation of question marks, let's go ahead and give it a name. Let's call that thing angular momentum. And then we're going to write down that so far we've just defined angular momentum as this integral thing that we were taking the time derivative of, right? It's the integral of r cross v dm. But we can simplify it a little bit because v, as we know, is omega cross r. And then we still have dm. And of course, I shouldn't forget that this is actually a cross product here as well. So in fact, what we get from this is the integral of r squared omega dm in the direction of r cross omega cross r, which if you go ahead and do the right-hand rule 2 times, you'll find that that's back in the direction of omega. So I'm just going to go ahead and turn this omega into omega vector to add its direction back into it. And what you'll notice is that the omega is factored out of the integral because it's constant for all of the points on this object. And what we're left with is the integral of r squared dm, which you should recognize as the moment of inertia about the axis. Right, that goes back to our point over here that r measures the distance from the axis. So this is precisely what I promised you at the beginning of this video, which was that L equals I omega is a conserved quantity when you have a rotating object. But what about a system that's rotating and moving at the same time? What do we have to change there? Well, just like we did before, we can start from the same place, right? We can start with this integral of r cross v, but now in this second case, v isn't just omega cross r, there's another term that we have to add, which is this overall velocity v0. That's the new velocity of every point on this disk. And so if we split this up into 2 integrals again, the first one is just the same thing we had before. We already know that it's going to give us I-axis omega. But the second thing that we have to worry about now is the integral of r cross v0 dm. But remember that v0 is just some constant vector with which this whole thing is moving together, right? It's the same for every point, so it can be factored out of this integral. And what we end up with is the integral of r dm. So that whole integral cross v0, we can factor it out like that. And the integral of r dm is again something we've already seen. That's the position of the center of mass multiplied by the mass of our object. So in fact, what we get is this angular momentum now is not just I omega, but you also have this contribution of mass times the position of the center of mass, cross product v0. Now, sometimes instead of dealing with this quantity v0, because maybe you're not given how fast the object is moving as a whole, it might be easier or more convenient to deal with the velocity of the center of mass. So we can rewrite this expression as Ix omega plus m RCM cross, and we can expand this quantity v0 by saying, well, really, this is just the velocity of the center of mass minus omega cross r center of mass. And that's just because if you flip this around, you get the velocity of the center of mass is v0 plus omega cross r, which is just the whole overall velocity plus the velocity contribution from rotation. So that makes sense. And what we end up with, if you do these right-hand rules again, is Ix omega plus m RCM cross VCM, that's the first term, minus m RCM squared omega. But guess what? We have 2 terms with omega in them, and if we factor it out, the coefficient is going to be I-axis, right, the moment of inertia about the axis, minus m RCM squared, minus m times the distance to the center of mass squared. And if that rings a bell again, it's parallel axis theorem time, right? That quantity is just the moment of inertia with respect to the center of mass axis. So we can write this in a much neater form. This is the moment of inertia with respect to the center of mass axis times omega plus m RCM cross VCM. And the physical interpretation here is just as nice as it was in the case of kinetic energy. What this is saying is that the angular momentum is just a sum of the rotational angular momentum about the center of mass, that's this ICM omega term, plus the angular momentum of the center of mass. That's the second term, which depends on how fast the center of mass is moving and where it is. Now, you'll notice that if the center of mass isn't moving at all, and all of the rotation is just around it, then we recover L equals I omega. On the other hand, if there's no rotation, and something is just moving in a straight line, you can still have angular momentum because there's still this second term that comes from linear motion, right? You get that L equals m times this cross product of distance cross velocity of the center of mass. Now, previously, this distance was defined from some axis of rotation, so obviously that interpretation doesn't make sense now, but you can still have an angular momentum with respect to some particular point, or some particular axis, even if nothing is rotating about that axis, and that quantity is going to be equal to mr cross v for something that's not rotating. But in the most general case, you have these two contributions of the rotational angular momentum, I omega, and the linear angular momentum, mr cross v. Now, a really important side note that I can't help but mention here is the implication of these equations for dynamics, or in other words, the relationship between torque and angular acceleration. See, in both of these cases, torque is just the time derivative of angular momentum, by definition. But in the first case, when you take that time derivative, you get torque equals I alpha, exactly what you would expect for rotating objects. But in the second case, when the angular momentum has rotational and linear contributions, taking the time derivative gives you torque equals I alpha plus this time derivative of mr cross v. Which means if you're calculating torque about some axis that isn't through the center of mass, then any acceleration of the center of mass will give you another term in the equation. In other words, you'll have torque equals I alpha plus something else that you can calculate by taking the time derivative of this formula directly. So that's something to be really careful about when you're doing physics with objects that are rotating and moving translationally at the same time. So with that said, let's go back and summarize the key takeaways for all three conserved quantities that we talked about in this episode. First, we talked about energy. Now, obviously, there's always a potential energy component to every energy conservation law, but what's new to rotating systems is that the kinetic energy can now be expressed as a combination of two parts. The first is translational kinetic energy, which takes into account the translational velocity of the center of mass of your object. And the second is rotational kinetic energy, which takes into account the rotation of your object about the center of mass. And it's important to remember that this applies even if the physical axis of rotation doesn't go through the center of mass. This equation that we derived still uses the moment of inertia about that center of mass. And that's a little bit counterintuitive, but you can go back and trace through the math exactly why that is. We also talked about momentum and angular momentum. Now, not much changed in the case of momentum, except now we're realizing that when we say p equals mv, the v we're referring to is the velocity of the center of mass of our object. And that lets us not get confused when we're dealing with rotating objects for which every point on that object is moving at a different physical velocity, right? All we need to think about is the velocity of the center of mass point. Now, angular momentum was a new concept, and ironically we found that there are two components to angular momentum. The first component is a rotational component, which takes into account rotation about the center of mass. And the second component to this quantity, even though we're calling it angular momentum, there's also this linear component, mr cross v, which takes into account how fast your center of mass is moving and what its perpendicular distance is from whichever axis you're measuring angular momentum with respect to. And that's actually a crucial distinction, right? An object inherently has a momentum, right? You can just say mass times velocity equals momentum, and that's just a number. But there isn't an angular momentum that an object can have because it varies depending on which axis you measure angular momentum with respect to. But even though that can be a little bit more confusing, that can also be a lot more powerful because you're always free to choose whichever axis you like, and in a lot of cases, you can find an axis about which there are no torques, and then you can use conservation of angular momentum about that particular axis. And the good news is that until we consider more complicated three-dimensional rotations, this is actually as general as these conservation laws are going to get. We're not going to be coming back every week with a new episode saying, oh, but in this case, you need to make your conservation laws more complicated in this way and that way. No, this is it. If you know these equations, then you can fully master conservation of energy, momentum, and angular momentum for any moving system, as long as its rotation is restrained to one axis. So I hope you guys enjoyed this episode. Drop a like if you liked it, leave a comment if you have any questions about anything we covered here, and I will see you in the next one.